Hi everyone, this is going to be the final class for Digital System Design course, and in this class we'll talk about computer design basics. When I prepared this slide, I didn't know what to include, as this subject matter is quite comprehensive and inclusive of a lot of design and electronic components. But I must tell you that most of the figures and the documents and some of the reference arguments are from the chapter 9 of Dr. Mano and Kime, Logic and Computer Design Fundamentals, published by Pearson, 4th edition, 2008. You know, the computer has revolutionized our generation. And once upon a time, there were computers, and computers were quite important. They were used to handle the computation needed for businesses. You know, help individuals create contents or documents, etc. After the invention of internet, the revolutionary aspects of computers have been emphasized because the connected network of computers has shown the potential for great computation power. It also enabled human beings to communicate efficiently. As the mobile technologies evolved in the last decade and the use of super slim and small chipsets led to a tremendous proliferation of computer utilization in our society, despite they appear in different form factors such as cell phones, etc. in today's world. In today's lecture, we'll discover some of the fundamental design principles of a computer. One of the most important notions of computers is the instruction set architecture, abbreviated as ISA, which at the lowest level specifies computer's appearance to a programmer who usually oversees the activities of computer at a higher level. Computer architecture is a high-level description of the hardware implementing the computer derived from the ISA. The architecture usually includes additional specifications such as speed, cost, and reliability. It is also important to mention that ISA serves as an abstraction layer between the software layer and the hardware layer. In other words, a gateway to the hardware. For example, compilers, which are known as translation softwares, takes the source code and converts it to machine or assembly language. This language contains register transfer level instructions, and these instructions have their corresponding binary instruction, and this is, of course, architecture dependent, and these instructions are executed by the central processing unit, or CPU, and finally the output is stored or displayed. A simple computer has three basic components: a data storage unit, which usually consists of a bunch of registers, a data processing unit, which could be an ALU, arithmetic logic unit, or a more complex functional unit, and a control unit that generates control signals for these components to move data and execute instructions. Apart from the memory, there are two major building blocks of a CPU. These are called Datapath and control unit. Datapath is responsible for all the data manipulations, which include register transfers, arithmetic, and/or logic operations on the registered store values. It also has a set of control interfaces, which are quite design specific. Control unit is basically the combinational or the sequential circuit that produces the necessary control signals for the data path. The inputs to the control unit is the ISA control sequences that are decoded in the control unit to generate meaningful set of control signals. Control outputs consist of halt or done type of signals to indicate the successful completion of an instruction. Control unit is also connected to instruction memory from which it reads instructions and fetch them for execution. Control unit can be programmable or non-programmable. These programmable units are known as microcoded and non-programmable ones are known as hardwired. On the other hand, Datapath has certain inputs and outputs for data memory, where the data is stored for processing. We'll explore details about these units in this class. It is best to consider the data path through an example, and this slide shows a data path example, which consists of register file and a function unit. A register file contains 4 parallel load registers named as R0, R1, R2, and R3, and 2 multiplexers for register selections. These are named as A select and B select. There is also a decoder to select for destination register. Multiplexer B or mux B is used for external constant input, and bus A and B can be used for address and data output. That's going to be clear when we discuss the control unit. So don't worry about it right now. The second component of the data path is the function unit. The function unit performs all the arithmetic and logic functions. This includes ALU, a shifter, and a mux F for output select, and we use G and H to select between different functions of the ALU and shifter. The output status signals will be covered later, which are V, C, N, and Z. Multiplexer D, which is outside of the functional unit in the figure, is used to select the input data, if any, otherwise the output of the function unit is selected. The datapath is used for data manipulation, as we mentioned before. For example, consider the microoperation R1 plus R2, and the result is stored in R0. This is called microoperation. To be able to execute this microoperation, we need to select A to be 0, 1. This will place R1 on bus A, and set B to select 1, 0, and mux B or MB select to 0 so that R2 contents will be placed on bus B. Let us assume 0, 0, 1, 0 operation to correspond to binary addition in ALU. Then we set G to be equal 0, 0, 1, 0 to add the contents of bus A to bus B. To place the result on bus D, we set MF to 0 and MD to 0. Once we load enable and select the destination to be 0, 0, the contents of bus D will be stored in R0 at the next active clock edge. You know, we can use the same circuit and perform different micro operations. For example, MF is set to 1, help us execute shift operation, and MB set to 1 applies a constant. The latter could be useful to load an input to one of the registers. We can initiate memory read and write operations by setting the register load enable to 0 and load bus A with the data address and load bus B bus B with the data to be written. There are basically 4 types of microoperations: register transfer operations, arithmetic operations such as addition and subtraction, logic operations such as XOR and AND, and shift operations which can be used in multiplication and division operations. Arithmetic logic unit is like the brains of the computer. We can perform arithmetic and logic operations in this processor unit. As can be seen, implementation of arithmetic component is based on an n-bit parallel adder. The B logic basically does the necessary manipulation to change the input B to an appropriate output Y, such that the adder output is one of the desired outcomes listed in the table, which is shown below left. Depending on the C-in value, one of the 8 operations can be performed by the arithmetic unit. There is also an n-bit logic operation unit which can perform AND, OR, XOR, and complement. The select inputs S0 and S1 selects one of those logic operations, and as a result of this, corresponding logic function will be performed. The select input S3 chooses between the arithmetic operation and the logic operations. The 2 status outputs C and V represents the carry-out value and the overflow detect output respectively. As you can see, the arithmetic unit can add, subtract, increment, decrement a given binary number. We usually assume signed numbers in 2's complement form when we perform arithmetic operations. Shifter is also another useful logic in the functional unit, as it can be used to perform all multiplication operations and division by 2 very efficiently. Here is an example 4-bit left-to-right shifter that can be based on select inputs shift to right and left. If the select inputs are 0, 0, the input is unchanged. The I sub R or I sub L are serial inputs for right and left shifts respectively. They're usually set to logical 0 values for almost all practical matters. Although binary shift operation is easy to understand, when we deal with signed numbers, the shift operation must be compatible with the requirements of the arithmetic operations. That's why we call it arithmetic shift. Arithmetic shift is used for signed numbers. The left shift occurs when a signed number gets multiplied by 2, and the right shift occurs when a signed number gets divided by 2. One of the differences of arithmetic shift compared to usual binary shift is that signed bit must be kept at all times. So the right shift of bits occur whereas the signed bit shifts onto itself as shown in the figure. So we don't get rid of the signed bit. The problem with the left shift, which is used to perform multiplication operations, is that the problem of overflow can occur. The XOR operation is used to detect the overflow as shown at the bottom of the slide. V is the status bit to indicate whether any overflow happens when we do shifting. So the Datapath consists of two basic modules. One of them is called the register file and the other is the functional unit. Register file acts like a memory based on clock flip-flops. In this slide, we redraw our Datapath using two sub-blocks, namely the register file and the functional unit. In this generalized block diagram presentation, we have 2 to the m registers, 3 register address inputs labeled as A, B, and D. The load enable is labeled as write input. The function unit has 2 inputs, A and B. The FS input is the function select input. There are 4 status bits, V for overflow detect, C for carry out, N for negative, and Z for 0 indicators. If A is less than B, then N becomes 1, indicating A is less than B. If A and B are equal, then Z status bit shall return 1. N and Z status bits will be useful when we learn about conditional branch and jump type of instructions later in this slideshow. Let us explore the function select codes. That starts with 000 and goes up to 1110. The 1111 FS code, old 4-bit FS code, is not used. This table shows the corresponding MF, G, H inputs of the ALU and the shifter and the multiplexer select inputs. For each FS code, the corresponding microoperation is also shown. As can be seen, additions, multiplications, subtractions, as well as 4 major logic operations can be performed by the 4-bit FS code. Please pay attention to don't cares and how we come up with these. Using our simplification techniques from our previous classes and a background, we end up finding MF to be equal to F3 and ended with F2, and G to be equal to F, and H to be equal to F also, again due to don't cares. And these equalities establish the relationship between the FS select, the function select, and G, H, and MF select inputs internal to the design of the function unit. As you observe, the Datapath has many control signals, and if we produce those control signals at the right moments of time, potentially in a synchronous manner, we can end up controlling the whole Datapath and be able to perform execute an instruction per clock cycle. To be able to control the Datapath in a controlled manner, control signals must be organized into something called code word. This way, for each given instruction, the control code word is generated by some circuit called the control unit and uses wires to apply the control signals at the appropriate inputs of the Datapath in each clock cycle. Here is an example control word for a Datapath which has 8 registers. The first 9 bits cover the destination address, source A, and source B register addresses. The MB, MD are multiplexer select inputs. The FS is the function select, is the 4-bit function select input. And finally, RW is the register write or enable signal. This control word contains 16 bits. However, as you add more selections and control inputs unit inputs to the Datapath, you will have more to control, and which will extend this code word to more bits. This slide is given to walk through some of the necessary control code words that need to be generated to be able to perform a given microoperation. I will explain the first microoperation shown in the first row. The rest is going to be left as an exercise. To be able to work with registers R2 and R3, we need to set source A register address to 010 and register B address to 011. The order matters because the second register in the instruction must be on bus B to be converted to 2's complement and then add 1 to get 2's complement and then for subtraction, get ready for the subtraction. Since the microoperation writes the result on R1, the register R1, the destination register address must be set to 001. To load the register content of R3 on bus B, we set MB to 0 and FS is set to 0101 to choose the operation A plus B prime plus 1, which is nothing but subtraction. The MD input is set to 0 to select the function output. And finally, we set RW to 1 to write the output on bus D, and then to register R1. As you can see with this microoperation, the code word entries don't cares. But with other microoperations, you may have those don't cares. In that case, you can simply assign any logical value to those don't cares since the outcome of the Datapath will not change. Let us have a short introduction to control unit and its relationship with the Datapath. The control unit has 2 major components. These are the program counter and the instruction decoder. The program counter keeps the addresses of data locations in the instruction memory. This memory could be a random access memory or read-only memory. Unless we use special instructions to make the program counter jump from one location in memory to another, In each clock cycle, upon the completion of an instruction execution, it's incremented to point to the next location in memory. In other words, the next instruction in memory. There are also instructions that make the PC jump and branch. On the other hand, instruction decoder decodes the incoming instruction and produces the set of necessary control inputs for the data path, data memory, as well as the program counter. The instruction decoder is basically telling other units what to do in the next clock cycle. The data memory block stores the data to be processed. The write enable signal of the data memory is controlled by the instruction decoder as well. Data path and data memory are in close communication, as the data path processes the data stored in the data memory. The instruction set architecture defines the format for various operations handled by the computer. The picture shown here is a high-level overview of the interaction between different units, and we mainly focus on single-cycle hardwired control. In other words, the control could have been done using sequential logic as well, but here is the hardwire and it's combinational. Finally, you can realize that data and instruction memories are physically separate. This architecture is known as hardware architecture and is common for single-cycle computers. Let us review the three well-known instruction formats. The register format has 7-bit long opcode. So instruction format consists of 4 fields: opcode, destination register, source A register, and source B registers. And opcode is generally 7-bit long, and 3 bits for destination register, 3 bits for source A, and 3 bits for source B. This makes up 16-bit long instruction. You can execute ALU-based instructions using register format as shown below. The second format type is known as immediate. In this case, the source B is replaced by a constant operand value, which can take values from 0 to 7. Immediate format can be used to add constant values to particular register content, as shown below. Usually, registers store more than 3 bits. In that case, a zero fill logic should pad zeros at the appropriate location before storing the result in the destination register. The third format is the jump branch, and which is explained next. ISA jump and branch instruction is a bit tricky and involved compared to the other two instruction formats. Let us spend a bit more time on it. Jump and branch format replaces the destination register and source B addresses with the address bits, which is a 6-bit signed 2's complement number to be added to PC's current value, conditioned on the contents of source A register. Jump and branch instructions are used to change the sequence of instruction execution. For example, if the contents of source A register is 0, then the address field of the instruction is added to the current value of the PC, the program counter. On the other hand, if the contents of source A register is negative, we could perform the same operation on the program counter as well. These two are called branch on 0 and branch on negative. In case of jump instruction, the contents of source A register is the new value of PC. In case of register and immediate instruction format, the program counter always increments, as mentioned before when we discussed the high-level description of the computer. The program counter is controlled by a separate unit called branch control. In order to determine the next program counter operation or the next memory address, we need to look at the status bits of the data path, which are N, Z, C, and V. N and Z are used to determine the negative or 0 condition. V and C can be used to indicate, for example, bad accuracy of the computation. There are also 3 more inputs to the branch control, and they are PL, load enable, for the program counter, and JB is the variable to determine if it's a jump or a branch instruction that's to be executed. And finally, the BC input is used to implement the conditional statements, like for 1 branch for n equals 1, else increment. Or, for example, for 0, branch for z equals 1, else increment. The truth table for these inputs and the corresponding program counter operation is shown in the table at the bottom of this slide. After covering the program counter and its details, let's cover the instruction specifications with regard to instruction set architecture. Alright, so here's the complete description of the instruction specifications based on the various possibilities of the opcode section. If you look at the opcode, you will realize that you can perform a lot of different instructions by just changing the 7-bit long opcode section of the 16-bit long instruction word. This table is just a way of describing the operations and the mapping between the opcodes and the operations. You can, redefine these mapping some other way, and it would totally be valid. So this is a way of doing the mapping. Once you determine this mapping, then it's fixed for the rest of your design, and the instructions are executed based on this table. Let us give an example and assume that instruction memory contents are loaded by an external circuit. As you can see, using the table in the previous slide, you can realize that the first instruction word makes R3 subtracted from R2 and writes the result in R1. Then the program counter jumps to 35, from 25. That was 25 was the original program counter's value, and then it jumps to 35, and the instruction at address 35 is executed next. According to this instruction, the contents of register 5 is transferred to data memory addressed by the contents of register 4. You can also walk through the rest of the instructions to see how they are executed by the processor. Here is the complete picture of our single cycle hardwire control and plus the data path. As you can notice, the bus A, bus B can be used as address out and data out for load and store instructions. Instruction decoder is the next item in control unit, and which converts the instructions into a set of signals necessary to control the computer during the single cycle execution. If you remember, we used to have 16-bit control signals, and now we add 3 more for the program counter. These are PL, JB, and BC, and 1 bit for enabling the data memory, which is the memory write, MW actually. This makes up a 20 bits long control word. The instruction decoder decodes the given instruction specifications for the control signals. This decoding operation should not be too hard for you at this point, because you can use our combinational circuit background and use simplification techniques to derive the relationship between the bits of the instruction and the bits of the control word. So let us try to draw the connections between the instruction and the control word. First, we copy the destination, source A and source B address fields to DA, AA, and BA. This covers the first 9 bits of the instruction. Next, we need to determine the relationship between the opcode and the control signals. We first notice that other than branches and jumps, the function select is given by the 10th, 11th, 12th, and 13th bits of the instruction field. If you consider 15, 14, 13, and 9, we can realize that MB is the 15th, MD is the 13th, and RW is the complement of 14th, and memory write, MW, is the complement of 15th, ended with 14th. PL is the 15th bit, ended with 14th bit, and finally JB and BC are given by 13th and 9th bits of the instruction. These expressions or functional relationships can be derived from this truth table. However, the 9th bit is also the last bit of the function select, the FS0. In order not to contradict with FS functionality, we need to differentiate FS0 from BC, which is equal to 9th bit of the instruction. It can be observed that if we end PL prime with 9th bit, we essentially be focusing on the functional unit where we use FS bits actively. Therefore, we set FS0 to 9, ended with PL prime, and the rest of the bits of FS equals as described in instruction word from 12 to 10. Using this argument, which was mainly based on the don't cares, we finally reach at a very simple combinational circuit diagram as shown in the slide. If my argument seemed a bit complicated, I would recommend you draw a big truth table with all those don't cares in place and try to use Carnot maps to simplify it. I'm sure though it will be very, very tedious. Anyways, once you figure the transformation of the instruction bits to control word, this would basically complete the design of the single cycle simple computer. Finally, I want to mention about the limitations of the single cycle computer. First of all, you might guess as the complexity of the operations required by the instructions grow, it will become very hard to complete the operation in a single cycle. And we want our computers to run fast, but yet this requirement will be transformed into a higher clock rate. Considering the worst case delay path, the rate of the clock will be limited by a single cycle time, which will be governed by the worst case delay due to running a particular operation. There are advanced techniques to deal with these issues, such as multi-cycle computer. In other words, execution of an instruction is not restricted to single clock cycle anymore. And one of the other approaches is the pipelining, which means you do not need to wait for a single instruction execution to finish to start another execution, and that will make instructions work in parallel. These advanced topics are out of the scope of this class, but they will be covered in computer organization and computer architecture classes. So in this class, we covered an overall design of a simple computer that consists of two main components called Datapath and control unit. We have seen that coming up with the best computer architecture is heavily dependent on the choice of the instruction set. The experience with the best set of instructions is usually attained through long years of experience, yet we have shown a well-known and used basic design methodologies that leads us to an understandable and neat design of a single-cycle hardwired control and controlled computer. We have also mentioned about limitations of the single-cycle computers and give you two advanced techniques to remedy, namely the multi-cycle architectures and pipelining, which are usually subject matters of computer architecture classes. You'll hopefully cover those topics in one of the future classes of computer architecture. And again, please feel free to drop any questions you might have about today's lecture into my email box, and I'll be more than happy to help you with your questions. Thanks a lot.